Chapter 5 will be all about distribution functions and what they can teach us about the underlying data. In the first few lessons, we will again turn our attention to the normal distribution, whereas in later parts, we will meet entire new classes of distribution functions. In a sense, this fifth chapter will provide us with the last insights that we need to be able to fully grasp the ultimate tool in statistics, namely statistical testing. So let's get into the slides and start with a brief overview of what we will learn. We start with the normal distribution function and try to link its statistics that we can compute with visuals on its histogram. Now, doing so will teach us new concepts such as percentiles, data intervals, and sigma levels. And this will bring us to the cumulative distribution function, which is an alternative visualization to represent these new concepts. And by then, we will have had enough of the normal distribution function. And thereby, we will venture out and explore new types of distribution functions and in which real-life scenarios that you might expect them. So let's dive into it. And we will start with something that by now we are very familiar with, namely that the basic statistics are different between the population and the samples. But at this point, we can go a little bit further and also include the theoretical statistics. These are the values that we used in our Python function to actually generate our populations. And as we will see, even though our populations often have a lot of data points, such as 100,000, the resulting population statistics still deviate ever so slightly from the theoretical values that we use to generate them. And this is encapsulated in the table on this slide. We again have rows being some basic statistics, the mean, the variance, and the standard deviation, and the columns correspond to different data sets. The second column is the population, which we are familiar with 100,000 data points. Then we have a small population, or a sample, with a lot fewer data points. But now we include this first column, which are the theoretical values used to generate the populations. Now, as we can see, even though the variance and the standard deviation are equal between theoretical value and population, the mean deviates ever so slightly. The theoretical value we provided was exactly 0, but then if we generate 100,000 data points with this value and we compute its mean, then we see that we get 0.001. So let's now dive into the code and see how we can replicate this table. All of the code in this cell will be very familiar by now. First, we define the number of data points in our population, and also the number of data points in our much smaller sample. Then we create our normal distributions. But now, instead of providing the mean and the standard deviation inside these functions themselves, we define them up front just to make clear that these are indeed our theoretical values. So we want a mean to be exactly 0, the standard deviation or the scale in this function to be 0.5, and then the variance is simply the square of the standard deviation. So we take the standard deviation, we square it, and of course again we want to round this number up to 3 decimals. Now, as an aside, 0.5, which is the standard deviation, to the power of 2 is 0.25. So the variance will be exactly 0.25. And now we will use these values to generate our data sets. Again, the normal population will be numpy.random.normal. Our location will be our theoretical mean. The scale will be our theoretical standard deviation. And the size will be 100,000, the population size. Now the same for the normal sample. All exactly the same, except of course the size will now be the sample size. Now I know that in previous lessons we made our sample dataset by randomly taking a subset from our population dataset, whereas here we just generate an entirely new dataset just with a smaller number of data points. Now this basically boils down to the same procedure. The only difference is that this sample set might not include values that are actually in our population set. But this is of no consequence for this notebook cell. So now that we have generated our populations, we can compute our statistics. And this is done in exactly the same way as before. The empirical mean for our population is our normal population.mean. Empirical variance for a population is the variance of our normal population, and the same for our samples. So we have the mean and the variance for both the population and our sample. And of course, we have the same for our theoretical values. Now we want to bring all of this data together in a nice data frame that we can use to compare these values. And also this procedure by now will be quite familiar to you. First, we define a dictionary that brings together all of the data that we want in our data frame. The keys in our dictionary will be the column names. We have a theory column, a population column, and a column for our sample data. Now, the values corresponding with each key are the values that we will get in our eventual columns. So therefore, it is important to always keep the same order. We have the mean, the variance, and the standard deviation. And the same can be done now for the population column. And thus, for our population column, we first have our computed population mean, and we round it up to 3 decimals. On the second place, we have our population variance that we computed, which we also round up to 3 decimals. And of course, the standard deviation we didn't compute explicitly, so we will do that here now. Now remember that the variance is the square of the standard deviation, and thus inversely, the standard deviation is the square root of the variance. Thus, we take the variance that we computed for our population, we take the square root of this number, and then we again round it to 3 numbers. And thus we keep the same order: mean, variance, standard deviation. Now we can do exactly the same for our sample. Then we create our data frame. So we say df is equal to pandas.dataframe. We provide our data, and the index will again be our mean, variance, and standard deviation in this order. Then we can display this data frame by just putting display df.head, and we can run this cell. And this brings us to a familiar site. We have a data frame where the rows correspond to some basic statistics that we computed, and the columns correspond to different data sets. Now, however, we have an additional column, the theory column, where the different values are the theoretical values that we used to generate our population and sample. Now, if we run this cell a couple of times, then we see in the last column that our statistics for our sample change from run to run. And this is nothing new. In fact, we already know that the sample statistics will be different from our population statistics. What we do see, however, is that also our population statistics will ever so slightly change from run to run. The only thing that remains constant are the values in the theory column. But this is of course because we define them to be the exact same numbers for each time we run this cell. Now the changing of our population statistics each time we run this cell shows that even though our population has 100,000 data points in it, this still allows for a little bit of wiggle room each time we generate a new random set of 100,000 data points. To fix this issue, we can add 2 zeros and look at 10 million data points and see whether or not our population statistics now also change from run to run. Now, apart from our data frame being generated in a little bit more time, because now we have to generate 10 million data points, we now see that our population statistics are indeed identical to the theoretical numbers that we used to generate these populations. And this showcases that while 100,000 data points might seem like a lot, if you want to get some really precise results, then you will need a lot more data points. What we want to do next is we want to think about how we can link these quantities, these basic statistics that we computed, to a visual representation of our distribution. Because by doing so, we might get a more intuitive understanding of these basic statistics. For instance, if we look at the standard deviation, we know that it is 0.5, but what does this number actually mean for our larger distribution? So let's find out. Now for the mean, this is very straightforward. Because the mean is just a single number, we can represent it on our histogram by just a single vertical line. And this gives us a very visual intuition about what this value actually represents. In particular, for a normal distribution or for any symmetrical distribution, the mean will always be at the exact center of our distribution. So even though we might not calculate the mean explicitly, we still will be able to easily pinpoint it on the histogram of our distribution. Now, this will not be the case for a non-symmetrical distribution, for instance, a skewed normal distribution. Here, we did compute the mean explicitly and visualize it with this dashed vertical line. However, if this wasn't there, then it would be quite difficult to really pinpoint down where the mean on this histogram would really be. Now, if you're curious how I generated a skewed normal distribution, well, let's briefly go into the code and see how I did this. And to do so, I needed to import a new function, namely skew_norm. Now, this skew_normal function generates random data in a very similar way that the NumPy random functions did. We just provide it with some parameters and it spits out a Python array containing all of the random numbers. In this case, the parameter that we need to provide is one parameter that is a measure for the skewness, and the other parameter is the number of random numbers that we want to generate. Now here, we want to generate two distributions, just to be able to compare them. Therefore, the skewness parameter, for the first one we take 6, and for the second one we take 0, so 0 skewness, and therefore we would expect a normal distribution. We compute the mean for both of our populations, because then we can visualize it on our histogram, and the remaining code is just plotting these histograms, which we did a lot of times by now. So when we do so, we see the following. We see on the left-hand side a skewed normal distribution, where the mean is definitely not in the center of our distribution, and on the right-hand side we have the skewed distribution, but with a skewness of 0, and thus unskewed. A perfectly symmetrical normal distribution where the mean lies exactly at the center. So for the mean of our distribution functions, we now have a very clear idea what it visually represents. So let's now turn to the variance. And for the variance or standard deviation, which indicates the spread of our distribution, we will have to do a little bit more work, because we approached the broadness of our distribution in two distinct ways already. Remember, at the start of this course, I showed you an animation of the probability density function of the normal distribution. There we learned that the broadness of this function is determined by just one parameter, this Greek letter sigma, which is the standard deviation. In our case, this was 0.5. We saw that if this number, this sigma, increased, that the shape of our distribution became much broader. And if this number decreased, then it became more peaked around the mean. But what does the actual value of sigma, in this case a standard deviation of 0.5, what does this value say about the underlying distribution? How do we get a more intuitive sense of this value? Now, another approach that we took in representing the broadness of our distribution is starting from the histogram. And on top of the histogram, we made a shaded area like this. And inside this shaded area lie all of the data points that lie within one standard deviation of the mean. And this then gives us a lower and upper bound of this region. So how do we now combine these two approaches together to get a more intuitive understanding of the broadness of our distribution? How do we convert between, on the one hand, a single number, this sigma, or the standard deviation, and on the other hand, a data range? Well, that is what we will learn in the next lesson, and it will bring us to percentages and also data intervals.